Well, hello and welcome again to our journey into number theory, and we're going to have a look at, continue on with our analysis of the average order of sigma of n. And as we saw, it's always worth seeing it again, it's such a lovely thing, that the sigma function, if you graph it, looks like this, and we want to average this out, and when you do that, we saw before, you get this remarkable phenomenon that it turns into roughly a straight line, approximately a straight line. And of course one asks, what's the gradient of, approximate gradient of this straight line? And just as a rough guesstimate here, I've only got very small numbers here, but the gradient's roughly 50 on 60, which is 0.833, and with, as I mentioned, pi squared on 12 is 0.822, and in fact the gradient of this line is roughly pi squared on 12, and that's what we're going to give a proof of now. So that is, we're going to show that the sum of the divisor function for n less or equal to x is equal to pi squared x squared on 12 plus big O x log x. So when we take the average of this, if I divide this by x, I get pi squared on 12x, that's the line, plus big O log x. So the error's only about of order log x. And the gradient of the line approximately is pi squared on 12, as our picture seemed to indicate. Well, the proof of it actually is not that hard given the machine we've already developed, and so this is what we're going to be proving. And the proof goes something like this then. So we start off with sigma sum of sigma n less or equal to x. And I'm going to write sigma of n, remember, is the sum of the divisors of n, so I can write that as sigma d divides n of d. And now I'm going to make use of that Dirichlet sum identity, that thing that turns these that enables me to take sums like this and rewrite them like in this form. So I'm going to use version 1 of that one, of the sums to divisor formula, number 1, and I can replace this as n less or equal to x d divides n is the sum n less or equal to x d less than x over n, and then sum d. Now the point is with that, we can sum this here. This is a very simple series here, because remember that if you take the sum from say 1 up to n of j, then this is just a half n plus 1, and this is the same sum, except now I'm summing up to the floor of x on n, so I just get a half n squared plus a half n, so there's my n now becomes the floor of x over n squared plus the floor of x. Now we can take the half out, and I can look at the dominant terms here. The dominant term is going to be this one, so this is really just x squared on n squared, plus we push the rest under the carpet, this is going to be big O x on n, so that'll take care of this term, plus any bits that we might have missed by going from there to there, because any such thing will be less than 1, and therefore I can put it into the big O x on n. Now we take the x's out, I get x squared on 2 times this sum, and then when I take the sum of this, then I'm just going to get big O, take the x out, sum 1 on n less or equal to x. Now we saw before that from that lemma that the sum of 1 on n squared is just, for n less or equal to x, is minus 1 on x plus zeta of 2, that was pi squared on 6, plus big O 1 on x squared. And this thing here, we saw that this sum was big O log x, and so the whole thing is big O x log x. Finally, we can look at the dominant terms here are going to come from the x squared on 2 and the pi squared on 6, which gives me pi squared x squared on 12. This is going to give me an x on 2. This is big O 1 on x squared. So the dominant term out of all that is the x log x. So I can bury all of that, the remaining terms, in this big O x log x. So that says that the sum of the divisors, the partial sums of the the sum of the divisors is this pi squared x squared on 12, and the error is about x log x. And if we take the average then, as I mentioned, if we take the average of this by dividing by x, we just get pi squared x on 12 plus big O log x. So that is a very nice result. And I mentioned that at the beginning of the next page here. I can get to it here. So the average value then of sigma x is this, i.e. it's roughly linear, which is, I think, quite an amazing surprise. Well, I'll do one more of these. We'll have a look at the order of phi of n, which is also very interesting to see what happens with our function phi of n. So recall that we defined mu of n by taking the reciprocal of the zeta function and expanding that out as a Dirichlet series, and we found that that was just mu of n on n to the s. In particular, if I put s to be, and this works for s bigger than 1, in particular if I put s to be 2 in, then this gives me sigma n equals 1 to infinity mu of n on s squared is 1 over zeta 2, so that's 6 on pi squared. And that means then that the sum n, so this is the sum to infinity, so the sum n less or equal to x of mu n on n squared is going to be 6 on pi squared minus the tail. So the tail is going to be the sum of all the other terms for n bigger or equal to x. And by our lemma above, we can write this thing, well, firstly we can write this as big O sum 1 on n squared, because mu is either 0, 1 or minus 1. And then we saw we had a formula for this one for the general case, and now I put s as 2 into that and I just get 1 over x. So that then gives me this little fact that sigma mu of the partial sums n less or equal to x of mu n on n squared is equal to 6 on pi squared plus big O 1 on x. Finally then we come to working out the true order, well, or the order of phi of the partial sums of phi of n, and this theorem tells me it's 3x on pi squared plus big O x log x. So once again the average order then, dividing this by x, is 3 on pi squared x plus big O log x, i.e. it's roughly linear, and the gradient is 3 over pi squared. So if you've got some computing skills, you can play with Maple and you can get Maple to draw the graph of this thing, and also get it to take the averages, and you'll find that you get roughly linear, and that's the gradient, 3 on pi squared. Now, how do we prove this? Well, again, we're just going to use the ideas that we've been developing. So we're going to use this fact here, that phi of n is the sum of over the divisors of n of mu d on n over d, which we proved earlier on. So now if I take the partial sums of these, then it's just the partial sums of this expression, and I can split this up into the sum n less or equal to x of n. I take the n into this one and leave this one alone. And I can now use that second Dirichlet identity, that second divisor to sum identity, which enables me to go from here, enables me to go from here to here. You just look it up, you'll see that's what you get. And I can then, the d's will cancel in here, so I just get sigma d less or equal to x mu of d times the sum q less or equal to x over dq. And then exactly as we saw before, we can sum, this is just a simple arithmetic series, its sum is 1/2 floor x over d into floor x over d plus 1, and as we did before, we can write that as a half x over d squared plus big O x on d. It's the same calculation we did looking at sigma. Finally then, just simplify this a little bit, we can take the half out, we can take the x squared out, I get mu d on d squared, And I've got the sum d divides x of functions of big O, so of order x on d, so this is x times sum 1 over d. And we worked out, we had a formula for this one from before. We saw this was 6 on pi squared plus big O 1 on x. And we saw before that this sum in here is big O log x, so this is big O x log x. Finally, we just look for the dominant terms. We're going to get 3x squared on pi squared. Here I'm going to get big O x, and big O x is smaller than big O x log x, so I can just bury that inside there. And there's our lovely formula for the partial sums of phi of n, from which we can get the average. Well, you can do this with other functions which you might like to experiment with and play with a bit. I thought I'd just finish with a couple of a little interesting corollary here, and it says that the probability that two positive integers chosen at random are co-prime, so if I just pick two integers at random, the chance that they've got no common factor is 6 over pi squared. Now you will immediately be saying, hang on a minute, what on earth does it mean to get the probability? We've got infinite sample spaces here, so what on earth does this mean? Well, I'm being a bit naughty and I'll define precisely what the probability means in a second. So here's the sort of proof of this. So the number of pairs, firstly, of positive integers Rs, which satisfy 1 less or equal to R, less or equal to S, so R could be S, and less or equal to N, is given by n plus 1 choose 2. Now why is that? Because if you take the numbers from 1 up to n plus 1, and you choose two different numbers out of this set, and you subtract 1 from the larger of the two, then you'll have two numbers that satisfy this condition. So if you started off with two numbers that were consecutive, when you subtract 1 they'll end up being equal, and the numbers R and S will be between 1 and n. Okay, so that's the little clever idea there. You take two distinct numbers from this set and subtract 1 from the larger. The number of ways of doing that is n plus 1 choose n, which if you simplify it is a half n plus 1. There are other ways of thinking about it as well you might like to play with. Now also the sum phi I less or equal to n, equals the number of such pairs that are co-prime, because all you do is you fix this one here, call this I, the second one, and let I run from 1 up to n, and then the number of choices for your R is going to be 5i. So you take the sum of 5i for I less or equal to n, that'll give me the number of such pairs which are co-prime. So we can now define the probability, so you don't scream at me and say, what does probability mean in this context? I'm going to define the probability that two integers are co-prime by simply dividing this finite sum divided by, so these are the numbers between 1 and n, so I goes from 1 to n, and this is the sum of 5i divided by all the pairs. So this gives me the ones that are co-prime. This gives me the total number of pairs. Both of these are finite, and I then take a limit as n goes to infinity. Now we have a formula for this, which we just worked out before, and so I can substitute that in to this, and then do the division and divide, and then many of the terms go to 0, and I just get 6 over pi squared left. So I'll leave you to just plug the numbers in and show that's what happens, and so the probability is about 0.608. So in other words, out of every, so it's roughly 6 on 10, so roughly 3/5 of the time, if you just pick two positive integers at random, roughly 3/5 of the time the two numbers will be co-prime. By the way, you can generalize this a little bit. You might observe that 6 over pi squared is just 1 over zeta of 2. And you can do a similar analysis and show the probability, as I've defined it above, that if you've got n positive integers chosen at random, that they are co-prime, is just 1 over zeta of n. So this is a special case of a more general result. Finally, I just note here what are the averages of mu and lambda. Well, these in fact are much more sophisticated. So the average orders of these are much more difficult to determine and are in fact quite deep results, and we'll come back to these in a later section. Let me just observe here that the following is true. If we take the partial sums of mu of n, n less or equal to x, and divide by x and take a limit, we get 0. And similarly, if we take the partial sums of n less or equal to x of the von Mangold function, lambda of n, and divide by x, and let x go to infinity, we get 1. Now, each of these statements, remarkably, is equivalent to the prime number theorem that we will get to later. This is quite a remarkable fact. Furthermore, and this really is a surprise, this sum, if you add up mu n over n, this sum in fact converges. Well, that's not immediately obvious at all, because this mu can be 0, 1s or minus 1s, and there's just enough of each to make the thing converge. And what really should knock your socks off is that the sum is in fact 0. But this also is equivalent to the prime number theorem. And so we'll come back and have a look at this a bit later on. All I'm going to do here is just as a little exercise to show you that the partial sums of this thing are bounded. That is, for x bigger or equal to 1, the partial sums n less or equal to x mu n on n. You add up this sum, you get less or equal to 1. Now, of course, you know that if you put a 1 on here, then this sum increases without bound. But if you put the mu of n there, then the sum doesn't get very big. It's always less than 1. And the only time you get equality is if x is less or equal to 2. The proof of this is a little bit fiddly, but it's worth having a look at. And so here it is. Here is the proof of our theorem 3.15. So we take x bigger or equal to 1. I claim that this is less or equal to 1 with equality only if x is less than 2. Well, I'll leave you to check. Case x less or equal to 2 is trivial, so I'm going to suppose x is bigger than or equal to 2. And I'm going to introduce what's known as the fractional part of a number. So I'm going to write, you take a number y, you subtract off its, this is a real number, you take a real number y, subtract off its floor, and you'll get a rational number, or rather, not a rational number, sorry, you'll end up with a number between 0 and 1, strictly less than 1, and that's called the fractional part. So the fractional part of pi, well, you just take pi and subtract 3 and you get the fractional part. Now, we need to just observe that this sum, mu of n times the floor of x on n, n less or equal to x, for any x, this turns out to be 1. And this is not very hard to prove because you just observe the following. This sum here is equal to this sum, because I can just replace the floor of x on n. I just take all the integers less or equal to x on n, and every time I get one of those I put a 1, and that's going to give me the fractional part of x on n. So I can replace that with this sum here, and now again I can use this product to sum, this divisor sum identity number 2 applied to this one. In fact, going the other way, normally you go from there to there. Here I go backwards and write this. And I've just ignored the 1 here. So you end up with this sum, applying that. Now this inner sum we've looked at before, this is 0 if n is bigger than 1. And it's 1 if n equals 1. So if n equals 1, then this sum just collapses down to 1. So this sum here is equal to this, and it just equals 1. Okay, so I can now write down 1 equals this sum that we've just proven is 1. I can write this as the floor of this is the number minus its fractional part. And I can split this into two sums, so it's x times mu n on n, that's from this bit, minus the sum of mu n times the fractional part of x on n. Now we want to get our hands on this beast, and so I rearrange this and look at the absolute value of this. And that, from what we did above, this is equal to 1 plus this sum. Now remember that these numbers here, these are all between 0 and 1. And so I can write this as, I can use the triangle inequality on this and say this is just less or equal to that. Everything's positive anyway, so that doesn't matter. And this then is just 1 plus this, so this is 1 plus. Now I put n to be 1n, so I get the fractional part of x on 1, plus I've got the tail, which are the fractional parts of x on n, where x goes from 2, n goes from 2 up to x. Now remember, each of these numbers is less than 1. So this is less or equal to 1 plus fractional part of x, plus this is going to be this many terms, the floor of x, minus 1, because we started at 2. So I can just get that there. Now the 1's cancel, and fractional part of x plus the floor of x gives me back to x again. So finally that gives me, putting that together, that says the absolute value of x times this sum times mu n on n is less or equal to x. Now x is not 0, so I can divide, and there's the result that we wanted, that the partial sums of mu n on n less or equal to x is bounded, it's got to be less than 1. And in fact, as we mentioned, if you take the, if you let n go to infinity, sorry, x go to infinity here, the sum of all of these turns out to be 0. But that is a very deep result, which is equivalent to the prime number theorem. And that is the end then of chapter 3.